What's up, guys? New topic, energetics. We're going to look at the theory in this video. Before we start, please like, subscribe, share. I want to grow this channel so it can reach as many people and help as many people as possible. Let's get into it. So these words, endothermic and exothermic, you should be familiar with from GCSE, and you've just spoken about them in terms of bond breaking and bond making. Here we have to think about things in terms of our system and our surroundings. So here our system is our reaction mixture, and that might be particles of reaction that are dissolved in water, and we're looking at various things in there. The surroundings here are the water, okay? And what's happening is we're measuring the temperature change of that. So often we've got something like a polystyrene cup to insulate. We've got a lid, again, to insulate a set amount of water that we've measured. And we'll look at the calculations behind that afterwards. Now, with an endothermic reaction, the energy of the system increases. The energy in the surroundings will therefore decrease. So what we'll see is the temperature dropping. So we also have this energy profile diagram, right? So here you should be familiar with this. We've got our reactants and our products. And we can clearly see that our products have more energy than our reactants. This will be our activation, of course. We'll talk about that more when it comes to rates of reaction and things like that. And people get confused, right? The products have more energy than the reactants, so they expect this temperature to rise. But we need to think about this in terms of the system, which we're shown by this graph, our reaction mixture, and our surroundings, which is not represented by this graph, but we'll see the impact on this temperature change here. Now, exothermic is obviously going to work in the opposite way. This is a slightly different setup. We've got a spirit burner here, and we can light that. We'll have some sort of, probably a hydrocarbon in there that we can burn. It's going to heat up our water. This isn't going to be a glass beaker. This is going to be something like a copper tin, again with a lid. So we're insulating, we're reducing as little heat, as we're losing as little heat as possible. Again, this time, this is our system, right? This is our reaction system. This is our surroundings, okay? So in this case, in exothermic, X exits, heat energy is exiting the system and it's entering the surroundings. So here, with our system, our energy is decreasing. With our surroundings, our energy is decreasing. So here we'll see a temperature rise, okay? And again, we've got our energy profile diagram here. We've got reactants, we've got products. We can clearly see that our energy is dropped. And again, we'll know that this is our activation energy. So this is the sort of basics, all right? We'll come back to these when we look at experimental stuff as well. The next thing we need to think about are the definitions that we're going to use. And this is our sort of loose scaffolding for all of our definitions for formation, combustion and neutralization. These are the three that come up most often. So, and we have quite a few more that come up at A level, but we won't worry too much about that now. So for formation, the enthalpy change when 1 mole of, and you can probably guess, right? So formation, something's formed. So here is when 1 mole of a compound is formed from its elements. in their standard states under standard conditions, right? So it might be something like, the reaction might be something like CH4, which is methane, and we've, formation. So we've got CH4 that's made, and it will be made from carbon and hydrogen. In terms of standard state, standard conditions, we've got H2, and it's a gas, and carbon is a solid, methane is a gas as well. So this is the sort of example of a reaction that we could be talking about. Okay, we'd obviously balance that, so we've got 2H2. The only thing we need to make sure is we've got 1 mole of CH4, right? So that's formation. What about combustion? So for combustion, it's when 1 mole of a substance, it could be an element, right? So not necessarily a compound, of a substance is burnt in excess oxygen. Again, in their standard states, standard conditions. Let's go CH4 again, standard state, plus excess oxygen, O2, and there we're going to make CO2 plus H2O. We obviously balance that. We need 2 waters to balance the hydrogens. Now we've got 4 oxygens, so we need 2 here. But again, we need all our state symbols. Gas, gas, and standard state of water is liquid. So that's the sort of thing we'd have for combustion. Last one, delta H of neutralisation. So here, one thing neutralisation is always going to have in common is we've got water forms. So the enthalpy change when 1 mole of water is formed from an acid base plus base reaction. And again, in their standard states, under standard conditions. So a good example of that, HCl, standard state is AQ, plus NaOH. AQ makes NaCl, AQ, plus H2O liquid. And again, the key thing for us to remember, 1 mole of water. So if for some reason when we were balancing this we ended up with 2 lots of H2O, we'd have to halve everything else, and this is the only time where we'd be allowed to halve things in a standard chemical equation. So those are our 3 definitions with some examples as well. What I'd like you to give a go is this. Again, meaning of the term enthalpy of solution, label this diagram. Before we finish though, let's look back at the calculation from the end of last video. So past paper question for a back titration. Again, let's highlight those key points to start. So MgOH2, 40 centimetres cubed, 0.2 moles per decimetre cubed. In excess, 0.2 grams of our powdered tablet. We're given the reaction, which is very helpful. We're given the concentration of NaOH, the volume of that as well. And this is our finishing bit, right? So, first thing, let's construct our 2 tables. So, we've given that first reaction, so we've got MgOH2, and we've got 2HCl, CNV, and our second reaction, again we're sort of calculating our change. We should know by now we've got NaOH, it's a 1-to-1 ratio with HCl, CNV. Let's begin. So we start off by filling out the information for our first one. Concentration of HCl, 0.2. Volume, 40 over 1,000. and CNV, we do concentration times volume to work that out, and we get to 0.008. That's what we started with. We need to work out what we've got left over. So to do that, we look at our second titration. This time NaOH, we've got 0.1 as our concentration, and our titration is 29.25 over 1,000. Again, concentration times volume gets us to 0.002925, 1-to-1 ratio times 1, 0.002925. Now, this is our change. This is what we had left over, left to react. So we need to find out what reacted. So our 0.008 we've already worked out, minus 0.002925. And there we get to 0.005075. Perfect. Now we use our molar ratios. I need to divide this number by 2 because of our 2-to-1 ratio. And there I get to 0.0025375. Next step. Here we now need to use mass, Mr. Mole. So, MR of MgOH2, we've got 24.3, 16 and 1. So we've got 1 lot of 24.3 plus 2 lots of 16 plus 2 lots of 1, getting us to 58.3. Next thing we need to do, we need to work out our actual mass. So mass is going to be our MR times mole. Just worked out our MR, and all of this stuff was to work out our moles. So we multiply those values together, we get to 0.148. Now we need to work out what percentage of our original mass given that is. So we've got 0.2 grams. So we're going to do our actual 0.148 divided by what we had in the whole powder, 0.2. All times by 100, and there we get to 74%. Again, if you struggle with that, these come up very rarely. Also, you know, this is worth 5 or 6 marks. You may well pick up, you know, 1 mark here, 1 mark here. You know, even if you've got the wrong value, you can pick up a couple of marks here as well. Even if you don't get full marks here, there are ways to pick up marks all the way through. Hope you found that helpful. See you next time. Happy revising, guys.